If you look at the history of breakthroughs in science in general, big part of this was serendipity or luck. Luck doesn't mean that someone woke up and found something. No, someone was working towards that direction, but then they had an observation that led to some breakthrough in that direction, right? If you ask someone in the industry today and tell them like, I can reduce R&D cost by 70% and speed it up by 10x, they would say that this is impossible. But I think this is the avenue that people should start dreaming about. LLM for scientific discovery is still very, very, very limited. You cannot today reproduce what you're doing. Like a typical human scientist have reproducibility of 40%. That is an extremely low number to train AI on. Since 1950, we had only 12 to 18 breakthroughs. Each of these innovations actually cost the world something like $1 trillion.
Ahmed, welcome to the podcast. Welcome to Paris, in the beautiful sunny Paris today.
Yeah.
Look, today we're going to talk about the stack of AI for materials, what it really means, hypothesis versus actually building the materials. There's a lot to uncover there. We're going to talk about why AI is struggling once it leaves the digital world and, touches atom, basically, which I think is a very big change. We're going to talk about how to build a business around AI for material discovery and, why it actually matters. But before all of that, Ahmed, can you please introduce yourself?
Yeah, thank you very much for having me, Hugo. Really, really great today to be in Paris. One of these nicest days to actually walk in the city. So that's what I was doing the whole day, to be honest. So about me a little bit. I'm a chemist by education. So I did, PhD, master's, and all these kind of formal educations in the Utrecht University in the Netherlands, one of the biggest schools for actually heterogeneous catalysis in Europe and in the world, and that really puts you in a focus mood, trying to think about materials in a multiple or multi-scale lens, rather than on the nanomaterial or the industrial scale. But you also try to bridge the ones in between. But I also before that and after that, I worked a lot in the energy industry. So I worked in very large energy services company, and later in a very large world multinational EPC company, and that gives you a very different lens to look from to the world. It's not, and that's, I think, will be part of our discussion later. It's like great what you're doing in the lab, how that translates and how fast that translates to things that people touch is, and that's a question that you ask yourself every day when you are in these settings. So as a technology manager, I was responsible for scaling up technologies, and this is the kind of things you get to see startups every day, but then only a small fraction that actually makes something that you're interested in the industry. So that's the kind of lens that I was looking at working for more than 16 years in the industry.
All right, let's take a step back.
Yeah.
And help me understand, how do we discover material today? Remove AI, 10 years back, nothing of that existed. How do we discover new material?
Yeah. So the way we discover materials today is what we call, in a way, forward design methodology. So you kind of like, you have a thought about a certain new development in the world or in science that you are very much excited in, and you happen to be in a research group that there's funding, or in a company that have a certain R&D budget, and you say, okay, there are these metal organic frameworks. That's very exciting. I wanna know what's this about. Oh, it's very complex. Maybe that have an application would have an application for something that I'm working on. So you start first focusing so much on actually how to make that material in the best way possible, and then you spend actually most of your time not just perfecting making it, but trying to understand what you made. So I can tell you 80% of my PhD was just trying to understand what I'm making in the lab. And
so what do you mean? So basically, what you mix some powders together, and you're like, okay, what did I do?
Exactly. So in material science, not always, in fact, quite often that what you mix is not exactly what you think you're making, right? So kind of like there are even humidity, temperature, pressure, a small change in the temperature of the lab can actually change how these materials look like. And then even after you make them and then you characterize them, you put them in a certain reactor to actually test what they do, whether it's catalysis or battery or something else, or even semiconductor. And they usually change everything. They change shape, they change chemistry, not one time, 5, 6, 10 times even, right? Depending on the type of material. And then you struggle. And actually the world is today in the academic world or scientific world is trying to, it's still at the stage where how can I actually understand how material behave in a chemical reaction, right? So that's what we call operando or in situ characterization, right? And even after you do all these characterizations, comes the most interesting part now for the application, which is, does it actually do what it should be doing? So that's how materials look like. So forward design is first you spend a lot of time trying to make the material, and then you actually try to understand what it looks like, and then you try to understand what it can make.
And so basically what you're saying is that we're not able to really predict the material that we're going to be building. In other words, this is a bit of luck, really.
Yeah, so I have a theory on this, and I have two co-founders in the company, of course, Alex and Marcus. And what I was trying to tell them when we started the company is, if you look at the history of breakthroughs in science in general, big part of this, not the biggest part, but big part of this was serendipity or luck incidents. Luck doesn't mean that someone woke up and found something. No, someone was working towards that direction, but then they had an observation in parallel to that led to some breakthrough in that direction, right? And even in semiconductors, like the use of copper and all these kind of things was actually in a way, in a lucky incidence. So there is a world where we can in the future, and we can already now predict certain types of materials and make them. But what actually the other side of that world, the industry, the application side of the world is interested in is not really if you can make it or if you can actually say what you're making, how it looks like, is what it can do. And that's a little bit surprising to some people. It was surprising to me when we were actually scoping what we were doing. Is like, someone asked me when we were like, I was like, can we characterize it in the right way? How we can automate characterization? And then someone not from our field came and told me, do you even really care? Like, you actually, yes, you have a hypothesis of material that you make, and then you want to know what it looks like, so some information about it looks like, but you don't want to know everything about it yet. You just want to test it quickly. Does it actually do what you want? And if it doesn't do what you want, you don't have to spend a lot of time characterizing it. Just discard it and go to the next one.
That's basically like science versus industry. The scientists are very excited about what they've created because, that's a discovery and that's what they've been trained to do all of their life. And then the industry is just like, actually, does it do what I want it to do? That's the only thing I care about.
Exactly. And how well it does this, right? How well and how fast it can do it, and how cheap and how more efficient it can make my process. And then there comes the breakthrough part, which is, of course, I want to make a material that can make my process 2-3% efficient, which translates to some processes into 2-3 billion, bottom line revenue or a reduction in OpEx. But can it actually even create a whole new process next to one I'm making, right? And this is actually quite a rare event. So industrial breakthroughs are quite rare. I can ask you a couple of questions about that as well. And,
what are some of the industrial breakthroughs that we have in mind from the past? What are some of the big ones that have actually changed the industry?
Oh, there are so many. And I can tell you the latest one. The latest one was actually almost 20 years ago.
20 years ago?
Yeah. So that was actually a process that was developed by BASF and Dow. Actually, it's called HPPO, where that was not an incremental, that was a breakthrough in the industry. They managed to use something called hydrogen peroxide to oxidize propylene into propylene, actually propylene oxide, which is a material that we use on a daily basis right now, in a drastically new way. It enabled them to reduce OpEx by, I think, 25%, or a CapEx by 25%, OpEx by 35%, and reduce the wastewater by more than 80%. So everyone was like, it's almost a very clean process to make actually propylene oxide. Everyone was so excited about it. They took a lot of time actually to develop it, but these kind of events, unfortunately, in our world today are rare. That was the last industrial breakthrough that we had. That was in 2008.
Wow. Okay. Interesting. Well, look, that's perfect segue for me to ask you about Dunia and what you're trying to build. It feels like there is a lot of excitement today around AI for new materials. I think one of the big catalyst moments was when Google kind of launched their model and kind of said, okay, here's a list of, I don't know, was it like 200,000 new materials probably that you can make. But let's talk about Dunia. What is the thesis behind Dunia? What are you trying to do?
Yeah. So, in the simplest terms, you want to be able to build a system that instead of going through this in lucky events, you actually want to reach, let's call them still lucky events, right? You want to reach these serendipitous or lucky events more frequently, right? Which means that you want to design the search space in the right way, in an unbiased way, which is also a big problem that we can talk about later, how biased we are doing our search in general for materials, the world today. So you want to design a system that enable you to accelerate the frequency of discovery, right? And by that, of course, people talk about, okay, reducing time to market or reducing the R&D time or accelerating R&D by 10x and all these kind of things. If you ask someone in the industry today and tell them like, I can reduce R&D cost by 70% and speed it up by 10x, they would say that this is impossible. But I think this is the avenue that people should start dreaming about, right? How we can change. We are having so many pressures these days to invent new ways to live. Can talk about climate tech, energy transition, but also, reducing expensive materials in our processes and so on, making our lives more sustainable. So there are so many pressures and urges for us to discover new things that you want to define a process that's much more efficient and actually to reach that discovery and to, most importantly, scale it up. And that's actually what Dunia is very much interested in.
You talk about the excitement and the vision for a world where you can accelerate the time to discover new materials. Obviously, on the other side of the Atlantic, we see a lot of big companies coming out with like 300 million round for pre-seed, things that are quite crazy. I think some companies are right now raising at the 7 billion-ish valuation, so quite crazy. Can you make a bit of a landscape for me as to what AI for material discovery means? Because from my perspective, you have, like, we include a lot into it, and I think that it's very much of a different, like, scattered space. So explain to me, like, what are the different sectors? What are the things we're trying to make?
That's very, it's an important, and I can tell you it's a very difficult question. We can talk about that the whole day. So the biggest debate that I have was a team and was other co-founders and people around us is basically, what do we call this thing? What do we call this field, right? Like AI for materials is actually not exactly the accurate way of discovery or saying what we're describing this field. But let's just say it's AI for materials right now. I like to call it accelerated discovery or accelerated materials discovery. The essence of what people are trying to do, there are different schools there, right? And with these schools comes so many new words like sim to real, simulation to reality gaps, or world models, and like reasoning models and automation and so on. But in essence, there are three schools of doing this, of trying to accelerate discovery of materials. There is a school that says, okay, I am actually focusing, and these are usually very well-known or very good AI scientists, right? They probably haven't seen a refinery in real life before, but they saw ChatGPT, or they could also be the ones who co-wrote ChatGPT, and they kind of like, hey, this kind of like AI for language was very successful. We also have seen DeepMind and AlphaFold in proteins, which was a very unique case, right? Proteins, you only have 20 amino acids or so. And they were like, okay, can we actually expand the AI to kind of generate new formulas, right? And they are building that. They are building generative models to kind of like reason new formulas and basically building the AI scientist, right?
Is that basically like, is that LLM but for science? And is that really an LLM, by the way, or is it another type of model?
Most of it, I thought there are a lot of this also being built behind the closed doors. But what I know, what I have seen is that most of it is actually still LLM, right?
Okay.
So it's kind of like, in reality,
Is that a
it's a
good use of LLM?
ChatGPT, where you write, I want to run certain experiment, and it tells you, okay, maybe you can do this, right?
Okay.
LLM is actually for scientific discovery is still very, very, very limited. So we use LLM at Dunia, but we use it, for example, for pattern search, for organizing thoughts, for kind of like organizing some of the information that we get, but we don't use it to guide the discovery. To guide the discovery of something that's extremely complicated, like materials, you actually need much more than LLMs, right? And that's, some scientists are also going to that direction these days, right? Building world models, whatever, all these kind of like new words means I can explain later. Word mean I can explain later. So that's one school, right? I build generative AI, maybe I can link it with quick experimentation, but it's basically AI that can actually reason new materials. There's another school.
Well, so on the first one, so I understand correctly,
Yeah.
it's basically saying we stay on the computer. Like we never leave the computer. We run experiments simulated virtually,
Yeah.
but we don't leave the computer.
Yeah, so that's AI. There's also a school of that or a branch of that says, okay, I do this on a computer. It's still AI driven, but I can have a quick lab or a small robot or some quick iteration where I can make, a sample in a vial to basically verify what I'm making, right? Or a fraction of that. But it's still very much focused on the generative AI or the AI scientist, right? And then there's another school, and that school is actually an expansion of the theoretical chemistry school and DFT that was developed in the 1980s and based basically on quantum chemistry that was developed almost 100 years ago. And that school is, okay, basically the thesis there is, can I use the whole new developments of AI to run or to develop these very perfect computer simulation models that can reason and can build the perfect system for a specific process on an atomic scale all the way up. And basically, after I do that simulation, go to scale it up and actually give it to the industry, right? So that's like they are building the perfect simulation or the perfect theoretical chemist, right? That can understand how a system, let's talk about, for example, an electrode or a battery or a semiconductor or a catalyst, how they behave on an atomic scale, nanoscale, basically expanding DFT, density functional theory, to build these systems. And these would be the perfect systems that would potentially have, I don't know, close to 100% efficiency, close to 100% selectivity, very stable, and so on, right?
What's the exact difference between the first and second approach?
Yeah, the first approach, focusing so much on actually gathering information and data from literature. So it's basically a training model, right? So I want to have as many data as possible. I don't necessarily need to understand how the system looks like, but I want to know I have A looks like this, that's published in literature, and it can do that, right? So kind of like patents, literature, they can do this also like high throughput experimentation, academic like way in the lab, in the vial, they don't do it in a device level testing. And then basically the idea is that I want to have the highest number of data that I can train my model on. A second one, they do some training like that, but they are much more focused on how can I actually develop the methods that can understand how an active site in a material moves and behaves and looks like and scale up and so on, right? Then there's a third approach or the third school, which is that's the one that's closest to the industry, which is, okay, I want to build the system that doesn't only reason new materials, that doesn't only simulate a perfect model, it combines these two, but also combines them with an autonomous lab. Not autonomous academic lab or fundamental lab, but autonomous industrial lab. So instead of actually building one electrode inside a battery system, I build the battery system, electrodes, anodes, cathodes, electrolytes, connect them with all of them, and basically make these systems, make these electrodes in a very efficient way, synthesis way, like high throughput, and then test them in a way that the industry would understand. We call that device level testing. So, and the way, if you do this way, you have a very high quality data that's relevant to the real application. Then if you use generative AI or other AI applications or models to train them on, you will get faster to the industrial breakthrough. So you might say, okay, that third approach is very relevant, more interesting for industrial application, but it's also the most difficult one to build, right? So because you basically will build this highest level or largest database of industrial high quality, high quantity data that you can basically get that ChatGPT moment for the industry. But then in order to do that, you have to build these laboratories in a way that's actually corresponding to what the industry does. It's not easy to do that.
In which of those three approaches does Dunia sits today?
Yeah, so Dunia does the third one. So, and the reason that we are doing the third one is that we are coming mainly from the industry. So the majority of the team members have actually worked, decades in the industry, and we saw firsthand a lot of ideas that comes our way, but it doesn't really translate into applications that I can adopt in the industry and scale up, right? A catalyst that that looks, that works in a laboratory vial is a great thing. But a catalyst that actually works in a refinery is business, is revenue, and you want to get to the second one, right? And in order to do this, we had to first, although we come from the industry, but we had our own hypotheses. We started 2022, but we were scoping this way before that. We went to the industry again and we told them, here is our hypothesis of what we want to have. This is actually the first design that we have of an autonomous laboratory system. And we had, I think, 42 discovery calls with the industry all over the world, actually. And the result of that is that we scrapped the first design. We realized, that it's not going to work for the application that we want to have, because people basically was telling us what I'm just telling you right now is like some companies, very big names, they would say, okay, doing what you're doing right now is perfect, but it's not going to work for me. I'm never going to buy it because I want to buy something that work in a reactor, in a what we call in the industry TRL 5-6 technology readiness level, 5 and 6 or so. So we decided that first design is not going to work. Then we built a second design, which was actually our first laboratory, and that one where you can test it. I think back then you can test 16 different, was for electrochemistry, 16 different electrolyzers, device level electrolyzers per day. And now we have Iris, which can do 56, and we're scaling up further.
When you say 56, is that a high number? Just to put it into context, because if we go back to the first approach is probably predicting thousands of new materials per day.
Yes.
But you're actually, on your side, testing about 56 per day.
Yes.
Is that a high number in the industry?
Yeah. So first things first, a typical very good laboratory scientist can do something like 3 experiments per week, like full cycle experiments per week, which is actually a very good high throughput for a laboratory science. If you want to do this full cycle, so designing a system, predicting a system, and then going on synthesizing it, depositing it, and then annealing it, conditioning it for a reaction, and then running the reaction, and then characterizing what's going on. If you can do this 56 times a day, that's for an industrialist, that's a mind-boggling, number. But if you put this into perspective of an AI that wants to train, AI needs tens of thousands to hundreds of thousands of these data, right? So what we do today is that we do 56 experiments per day, which makes a lot of companies very much interested in actually working with us because that's already a very high number for them. But then we also complement this with simulations still, but simulations, what we call dynamic descriptor simulations or machine learning force fields. So simulations that are representative to what actually the experiment was doing. For every experiment, we can do also tens of these simulations to cover the gap between different experiments in the search space. And this way you can actually complement real industrial data. You capture the data and the metadata have real provenance, but also have simulations that can support this. You feed all of this into world models or multimodal foundational models, and they can actually reason, provide chemical knowledge. So
if I simplify, is it basically saying, if I do one experiment with 1 gram of salt and then 2 grams of salt for another experiment, you're basically saying I can assess now what's going to happen if I put 1.5 gram because it's in the middle. Is that the rough estimate of what's happening there?
Yeah, in a way. And there's also some other ways to this, right? So you kind of like, if I'm using a certain formula that has certain metal loading, let's say 10% iron, 20% cobalt, and so on, and you tested 3 or 4 or 5 of these formulas, your simulation starts to also look around different metal loadings there of the same elements, right? And then it comes up with something that's actually very close to what you usually test in reality. Doesn't only do this for the efficiency, but it can also even do this for stability predictions and even cost predictions. So over time, it learns how to actually, refine the cost in a way that it actually looks at samples or materials that are cheaper in a way that can still give the same efficiency. This is approach, we believe that this is approach that can actually lead to faster and sooner to industrial breakthrough. Of course, you mentioned the other approaches as well, where, so, in a computer screen, I can predict hundreds of thousands of these. And that's, by the way, something we did in the beginning. So when we started, we were actually school number 1, right? And we realized that this doesn't work. And then we decided that we have to build a lab. Yes, but then another problem kicks in after you do these simulations, which is what we call sim to real gap, simulation to reality gap. That that in a nutshell means that whatever you're actually simulating on a computer screen does not easily, necessarily, actually most likely, doesn't translate to something that you can even build in a lab. It's usually a very interesting formula on a computer screen, but then it's not synthesizable, it's not stable. You cannot even know how you actually combine these materials together in a chemical lab today and actually make them. And even if you make them, they might not be even stable for 10 minutes in a reactor. And people have been talking about this, I think recently in the news a lot, because many of these, there was a lot of excitation, right, when these databases were released. And then recently, MIT and others were publishing, okay, this is actually a hype. Is this any good? Because we cannot make any of these materials. And there was a lot of criticism to that. So I think the right way to do this is you need to be able to close to the application as much as possible when you approach that field.
What do you think that you have understood that others have not yet? Because, your point is very much valid.
Yeah.
But if I were to be a bit challenging, more than $1 billion have been invested in startups that are doing the first approach.
Yes.
So a lot of people with a lot of money believed in it. That doesn't make it necessarily right. I agree with
Yeah.
you. But what do you think that you have understood on your side?
Yeah. So if you look at the history of venture capital and innovation in general, not necessarily the loudest or the richest company actually wins the race usually, right? So and that's actually something that we also have found in Europe a lot recently, and in the West, we come up with something that's great, and then, we build it for 15 years, and then suddenly you find out something from China that you have no idea about that's actually much more efficient, and you didn't even know that it existed, right? So kind of like I think who wins at the end is the ones who build something that's actually have the highest breakthrough potential and have the highest impact that people can actually touch and feel. Why did we all like ChatGPT when it came in, right? People have been talking about AI for 20, 25 years. Just before ChatGPT was announced, there was even a discussion about, okay, is this whole AI thing is dying, right? Because we don't. And then ChatGPT came and everyone got excited. We got excited because we actually could touch it. We could see the impact right away. Okay, I can write a message and it talks to me in a language that I understand, right? So companies, and I mean, not only in the AI for material space, but in general for innovation, those who succeed are not necessarily those who are having the biggest war chest. They are the ones who are actually tackling the right problem. There are so many reasons we can talk about this. I like to speak freely usually. So there are so many reasons why different companies raised a lot of funding. One of these reasons is that there are some people out there in the market are betting on companies who are building something similar to ChatGPT for materials, right? So the AI scientist in a way, like, oh, I can maybe build an LLM in the future that I can just ask it to make a new material, and in 10 years from now it can maybe make it. Those who are more closer to applications, they know this moment might come. This super intelligence for materials might come. It might take longer than people think because materials are so dynamic and we actually don't even understand a lot about how they behave today yet.
And the good thing about it is that if it ever happens, that's not a problem for you because actually you have the lab to try the experiments. In other words, the first approach could fit into the second approach, which could fit into the third approach, right?
Yeah. Yeah. So I always, when we chat internally and, during weekends, I also tell the guys like, in a way, the way we're building the company right now is like NVIDIA for semiconductors, because that's what's happening to us on a daily basis. So we had many of these companies who are coming up with amazing predictions. Ultimately, they actually come to us to be able to validate what they're doing, because I simulate something on a computer screen. I like it a lot. And then I publish it. No one believes in it. So what do I do next, right? I go to these guys to kind of like, they have the fastest way, the highest throughput way, not just for testing, but for making it to actually validate that, right? And ultimately, we actually very excited about what they're doing as well. So we're actually in a reality, we don't really compete, we talk to each other. And as I always say, it's not going to be one company in this space that wins. I think you need tens of these companies because material science is so huge. So there are so many different applications. My belief is that a generalized approach of AI to tackle all kinds of materials is going to be very, very, very difficult to achieve in the short or even midterm. But if you have different companies that are, market leaders in specific different applications or different verticals, I think this could actually scale much faster. But who knows? It's very dynamic these days.
Do you think that the future of this space is to have specialized companies that focuses on one type of material, one type of industry, and just do it super well, as opposed to have this kind of big ChatGPT moment. In other words, even for ChatGPT, it's interesting because now we're seeing more small specialized models that are, trained on less data,
Yeah,
but more specialized towards one specific task.
exactly.
Is that going to happen as well in your
And we
space?
use them, right? So there, we were chatting earlier before about certain, tools that can make very nice slides that, not
Oh,
other,
we can
not
mention
other,
them. Gamma is amazing. So,
exactly, no other tools like ChatGPT and Claude are great. We are all using them, but when we want to make great slides, we go to Gamma, right?
Mhm.
So it's ultimately that's a business model that's working quite nicely. And my view, I don't know exactly what might work and might not work in 10, 15 years from now. My hope as a human is that we want to be able to have a generalized model to do that will solve a lot of our materials problems. It's still far, far away from the moment that we live in right now. So, a great breakthrough would be if I can get this AI to invent something in my vertical. And that's already a massive breakthrough for the industry. And then the two verticals next to it. And that's actually what Dunia is doing today. So what we're trying to do is that we're not looking at one specific application or one specific material, but we are looking at verticals
Okay.
where we can
What are they?
target. So we started actually with catalysis. We started with electrocatalysis as use cases. We had some very nice.
What is a use case for
Yeah, so
catalysis?
we had electrodes. So we had something for green hydrogen, and then we expand from there. We did a lot of CO2 electrolysis as well. But then now we are also doing thermocatalysis. We are having some very nice commercial projects there. There are the vertical close to the catalysis, or mainly thin film. So electrocatalysis is actually batteries as well. So we have also a lot of very interesting, traction there, because the way we build IRIS, and by the way, IRIS stands for Intelligent Research and Innovation System. You have to be very smart building these laboratories. If you build them for one application and then suddenly you are interested in something else, you have to actually dismantle and rebuild, which means it's not only the cost that's a problem, which means when you build a new one, probably the database that you have before, the dataset, are not usable anymore. And that's a big problem. So we thought about this when we started, and the way we designed it is that you want to build these systems or these laboratories as modular as possible, so that if you're focusing on one or two, three verticals, in our case, we focus so much on thin films, which means translates into catalysis, translates into batteries, translates into semiconductor substrates, not exactly semiconductors, but they're substrates. And these are the spaces that we are focusing on right now. There are other things that use the thin films as well. And now we expand thermocatalysis, which is more powder materials and extrudates. Our system is very modular for these. So if I'm working today on co-development with a company that's doing catalysis, and tomorrow with a company that's doing actually like a device level batteries, we can do it with the same system without having to change anything. The only thing that has to change is that the agent has to readjust what kind of robots it will activate and what kind of robots is not going to be activated for testing the battery versus testing a catalyst.
That's actually leads me to a bit of the next section there. But what has enabled Dunia?
Yeah.
In other words, why wasn't it possible 10 years ago?
Yeah. So there are, I'm recently flying a lot. So when I'm flying, I kind of like sitting on a plane for, 10 hours, 11 hours. And I'm reading a very interesting book called Pattern Breakers by Mike Maples, very well-known seed investor in Silicon Valley. And he was talking about something that you just asked about, the inflections. What kind of inflections that happened in the market that enabled companies, certain companies or certain founders, teams, capitalize on these inflections and create breakthroughs, series of breakthroughs, not just one, but series of breakthroughs, like what Intel and Moore's law did for semiconductors, for example, and how you can actually capture these inflections. We had several inflections in the market over the last 10 years or so. The robots that we used to build 10, 20 years ago are very different from the robots that we build today. For chemistry and for laboratories, 10 years ago, 5 years ago, you could build a robot that can do one step. Now you can actually have a programmable robots that can do multiple steps, multiple very complex steps at high temperature, high pressure, in a very short time, in a very efficient way. So efficiency of how a robot moves and takes a sample and put it somewhere else in a micrometer, millimeter scale is extremely important, because you know what's the biggest problem for material science that made us actually not being able to use just literature data and train AI on them? reproducibility. You cannot today reproduce what you're doing. Like a typical human scientist have a reproducibility of 40%. That is an extremely low number to train AI on, right? So if that's one of the, we spend 1.5 years at Dunia fixing that part, right? How you can make not just one robot, but while you're building Iris, which is around 10 robots today, and they are all talking to each other autonomously, how you can make them, orchestrate them in a way that every movement of a robot is traceable, and every movement can be tracked and reproduced, and that is very, very important. We started from around 55% reproducibility, went into a death valley where we're kind of like very close to closing the company, to be honest. Like, okay, we cannot push it further. We cannot get high quality data. So let's just close it, right? And now we're actually at 92%. There are some things that we did there. And there are some people who came to the company who enabled that, you're right? Human resources and like that great talents are actually the biggest asset any successful company would be able to have. But
what
then,
are the type of people you need to be able to do that?
Yeah, so now we are at 92% reproducibility, which is exactly the type of data that we need to actually for AI. So you need robotics engineers, right? You need these guys who speak in, a certain language, engineering language, to speak with chemists who speak a very different language, and to speak also with software engineers, API engineers, orchestration engineers, AI engineers, who each of them speak in a very different language. I have to say, I'm still learning their language today. So every now and then I'm in a presentation or a meeting and someone says a word, I was like, okay, where did you come with this word? It's like, oh, actually, that's a technical term. We use it every day. So like all of these, when you put them together, and teach them, or start talking to each other in a language that's common between them, crazy things happen. And there's in our history in general in the world, there are instances when you get different peoples from different disciplines to sit with each other, these breakthroughs just usually follow. And there's a very nice book I would like to recommend called Idea Factory, that's discussing exactly this, what happened in Bell Labs and why Bell Labs have been able to come up with all these crazy breakthroughs in a very short time. Several Nobel Prizes give us the semiconductors and everything else, basically because they decided to do that. They built a place where they put engineers, chemists, physicists together, talking to each other on a daily basis, and breakthroughs followed. And that's what we're trying to do at Dunia today.
Okay. You mentioned that you have 10 robots. Can you help me understand exactly how that works together? So when we say robots, is that arms? Is that like, what type of robots are we talking about? How are they orchestrated? What have you built internally versus what's off the shelf? Because it feels like a lot of the value that you have from, or at least a big unlock that you have at Dunia, is being able to orchestrate these robots together.
That's one of the biggest advantages we're very, very proud of, is how you can actually orchestrate. So I mentioned earlier that there has been breakthroughs, inflections in robots, right? And then there's another inflection, which is people started to be able to actually put these systems on one dashboard, and let them transfer their signals to each other and to a system that controls them. This is way easier being said than actually being done. I can tell you this. And
so it's the orchestration of the robots that's the unlock.
Orchestration of the robots. You can imagine it of like building a brain that actually, points to one robot to do something. And when it's finished, that brain's still looking at it, tell another robot to take that sample or take that system and give it to another robot. And then this one stops working and then activate that one to start doing other experiments as well. So that is actually what orchestration means. There are different levels of that. There's a even crazier level, which is what I mentioned earlier was just sequential, right? One robot finishes something, the other robot starts something, the other robot starts something. Now imagine if you can do this also simultaneously. So the reason we can do up to 56 experiments per day or so is that we have one robot that does experiment number 3, while another robot finishing experiment number 1. And this is another level of complexity and orchestration that enables you, and that's the other power that I'm very proud of, that the team managed to make, enables you to have these high quality standard data being tested at an industrial device level. And then once you have these data and you prove that they are actually, high quality, and you capture everything on just not the testing and how they're made, but everything from the moment you actually predict them all the way to characterization, you feed that into, then AI becomes interesting. You feed that into AI, you feed that into simulation models, and actually starting learning much faster. So we always say like, oh, our system can learn 6 times faster. And one of the reasons for that is that you already have high quality data to do this. Another reason is that you can simulate what actually happens in the reaction.
Do you think you have the most advanced labs on Earth?
So I am quite proud saying that when it comes to industrial device level testing, I think we are one of the world premier company who actually built something like this. There are very sophisticated systems out there. There are people who are actually academic advisors to the company who build probably even more sophisticated systems for academic purposes. They didn't build them for throughput, but they built them for fundamental understanding how material science works. In terms of industrial breakthrough, I can, with some confidence, I don't know what everyone is doing everywhere in the world today, but the ones I know of, I can say that definitely ours is one of the most advanced in the world today.
That kind of leads me to something else, which is we hear a lot of thoughts about AI replacing people and labor. Is AI and robots going to replace scientists?
Yeah, so short answer, we don't think so. So I don't think, like, personally, someone might hear this 10 years from now and they might have said, oh, that was not right. But I do truly believe that the state of the AI today and the state of the AI in the next 5-10 years is not going to be able to replicate and produce new types of knowledge that can actually just simply replace scientists. Science is a very complex discipline. It's not language. It's a complex discipline that requires you to understand multi-scale, as I mentioned, multi-scale fields and connect, historical knowledge, but also try to reason. The scientist's job is actually extremely difficult in a lab. They are trying not only to kind of like predict the next steps that what they want to do, they are trying to predict the next step, but also understanding what might happen, imagine what might happen in a nanoscale, but also larger scale. We believe and we think, and that's the hope as well, is that AI will be able to enable scientists to do much more. When I was doing my PhD, I wanted to do many more things. Like my PhD is like 350 pages. Like people were complaining about how big it is, but it just captures part of the things that I was working on and a very small fraction of the things that I really wanted to do. I still dream about these things that I didn't do. And AI will enable us to do much more. To test ideas much faster. It enables us to actually be to do the functions that we were actually created for: supervision, like supervise, simple, mundane, or even complex but mundane tasks, right? And understand, trying to judge if these tasks are the right way, or do I need to actually design and supervise something that's even better? So I believe that's actually going to enable us to, have 6 hands, can do much more, can complement what we're doing. We don't really think that it's going to replace human scientists, at least for the foreseeable future.
And do you think that AI has a similar capacity to humans in terms of like enabling large breakthrough? Because it feels like right now AI is basically good at doing incremental steps, incremental discovery. But the human brain is quite interesting because it's able to imagine, right?
Yes.
Which I don't think AI is able to do today. The human brain is amazing because it can think through, 5 years from now or 10 reactions from now, what's going to happen, or maybe what's going to happen. We never know, but at least we have this ability to predict.
Yes.
Do you think AI is good for breakthrough discovery or only for incremental discovery?
Potentially in the future. So like people are talking about multimodal foundational models. We are building, a Dunia world model as well. And these models they are still very statistical models. They are like, as a status that they have today, they are still learning the knowledge of how chemistry or how physics works and all these kind of things. And they take the data and they are trying to deal with them statistically. And they are trying to, whatever you're saying exactly, extrapolate the next 10 experiments or so, right? So what AI is doing today, and I was, that's a very nice example from Marcus. I was chatting with him earlier, my other co-founder. You have a certain cat standing on a table, and you ask AI to do something about it, and they make another type of cat, right? Maybe they will make it with different colors, they will make it more beautiful and so on, right? Potentially what world models will start to think and do in the future about is like, you have a cat standing on a table and there is a hand at the edge of the picture. the world model will start thinking like, maybe that hand will, pet a cat, or that hand will move in a different direction. So it's kind of like not just copying something in a better way, but actually what else can happen there. Like the way that similar to how a human brain works. We are not there yet. We are developing this. There still needs to be a lot of breakthroughs in that field in order to enable breakthroughs in material science and chemistry, but it's developing in this direction. But also human mind is irrational. And that's the nice thing about it, right? So kind of like sometimes you're thinking, I'm talking to you today, I'm talking to you in that exact moment, and for no logical reason, I might be looking at my laptop. These kind of like irrational moments in the human brain can also lead to breakthroughs. AI don't know that yet, right?
Yeah.
So kind of like we are capable of having these jump or step edges in thoughts that we haven't yet been able to program in these codes. And that is, I find this quite interesting, how that might actually materialize in the future.
Yeah, we could get into that feasible kind of I guess it's a real deep discussion that we could have. But look, maybe let's go back to something that you've mentioned earlier that we didn't touch on, which is simulation to reality gap.
Yes.
We touched on it, but we didn't get deep into it. I'd love to understand more. So what you're saying there is that there is a big difference between what we can predict on a computer and what happens in real life.
Exactly.
How do we fix for that?
Yeah, so I can tell you today, with the technologies that we have in the world, like, if you are today using a typical density functional theory to try to simulate a system or a catalyst that's being deposited on a substrate or something like that, how it looks like, you can imagine a 2D slab, and the catalyst, the active site of the catalyst, or the catalyst itself, is like a sphere jumping on that slab. Okay, that's how we simulate these kind of things today. In reality, it's way more complicated. It's like a lot of step edges and a lot of impurities, and the catalyst itself is not a sphere. It could be so many different things, right? It doesn't really jump on a substrate and so on. So there are a couple of approaches where that we are doing at Dunia to try to actually tackle this. The first one is called dynamic descriptors. Professor Bia Adrian, his work at Dunia, is working on this. He's one of the people who actually developing actively these dynamic descriptors. And what these dynamic descriptors enable you to do is not to just build something or imagine or design a catalyst that's static, but it enables you to understand how these step edges and active sites on that system moves during a chemical reaction. So a chemical reaction, usually you apply pressure, you apply temperature, you apply voltage, and so on. So when you apply these things, a catalyst or a battery changes its shape on a nanometer scale like 5 or 6 times. Dynamic descriptors enable you to understand how these active sites change and what happens to the energy levels of these active sites. And that is very important. That's one of the breakthroughs that's helping us a lot to learn more. But then,
so what do you need for that? Do you need like sensors to be able to predict that, or is that purely on a computer?
That's still on the simulation side. So that's on computer scale. So you basically, what you do is that you develop a chemical knowledge, human chemical knowledge of how, for example, characterize how a battery works under a certain voltage. You measure it with electron microscopy and so on. So you develop that knowledge and you transfer that knowledge to chemical and mathematical equations, to an AI model or a simulation model, and this is what we call dynamic descriptors. So it starts to think in the same way as you doing the experiment, and then it starts to actually model how what happens there. That closes the loop, that closes that gap a little bit, but still the gap is still large. And even if you do these dynamic descriptors in every system that you're actually making, you are gonna use a lot of compute. Right, you are still gonna use a lot of that DFT, to do that, and it becomes a very, very, very expensive simulation.
Is that one of the blockers, by the way, today for discovering new materials?
That's definitely one of the blockers in general for theoretical chemistry. So you need to have much more compute, right? But there are certain ways to actually enable you to have shortcuts to do that. And that's the other thing that we are doing in the simulation side, we call machine learning force fields. In a very simple language, what this does is that it doesn't really do the full simulation of DFT. It actually does only the most interesting things, the most interesting parameters and functions that enable you to understand how these dynamic descriptors behave and energy levels behave, and then use these few data to actually complement the experiment, the experimental results that you have. And if you have these few data, but few accurate simulation data, and then also have a lot of high quality industrial device level testing data, that actually enable you to do these predictions way faster than when you do the experiment alone or you do a DFT simulation alone. That's what we have found.
Interesting. Is it like a patent that you own on that specific part? Like, how does that, is that something that's known across the industry?
That's something that's being developed across the industry.
Okay.
There are a couple of actually research groups and companies in the world. Most of them are actually in Europe who actually developed this. We have some patents in this space. We have some patents on the material side, but also in the robotic side and the algorithm and software side as well. So we're trying to protect this. But actually, the majority of these things are trade secrets. So you kind of like, if you publish them in a patent, people will know, and then it becomes very interesting. So kind of like you try to kind of like keep these, it's an asset for companies who are developing these dynamic descriptors that you actually want to keep them and use them to train your models. But it's one of the very nice inflections in the market that we are trying to capitalize on.
It seems like you have a couple of blockers in your industry. So actually, with that dynamic scripters, you might have solved something. But the other points that you've mentioned is one, compute and the cost of compute and the availability of compute, like having enough compute. Second thing is something you talked about briefly earlier, but I want to touch on again is data. In other words, it's hard because data comes from experiments, and experiments are run at best 56 times a day.
Yes.
How do we deal with kind of the lack of data? Because, ChatGPT works well because it was able to ingest the entire Wikipedia and internet, right? So,
Absolutely.
But it's not the same in your industry. How do we deal with that?
Yeah, absolutely. So data is the name of the game in this field. It's not just the data even. It's like I would just add few words for that high quality, standardized, highly calibrated data, not just for the catalyst or the battery, how it looks like, but how it was made. So AI needs all of that. They need the prediction to train on. They need the what we call the metadata or the provenance, which is like the history of how these materials were made, and they need also the characterization of these materials and their testing, right? All this kind of data. So you need a highly standard data to do that, and those who will be able to get these data and get them as much as possible closer to the reality, those who are the ones who are gonna unlock these breakthroughs. It's very difficult, I have to say. Like our solution to this is to build what we call gigalabs, right? So instead of actually doing, Iris today can do 56 experiments a day, full cycle experiments, closed loop experiments a day. But the dream is, can we do 500 a day? Can we do 1,000 a day? Which means that in a year you can do tenth of thousands of these, data, and then in a few years you can also have hundreds of thousands. And basically, the GigaLab is a concept which scales up on what we do in Iris today. So it's the same orchestration of different robots doing different things, but it's going to be much more modular, much more sophisticated orchestration. You can imagine it as something similar to the Amazon factories where you have these robots taking samples and parcels and so on. The GigaLabs for chemistry and for industrial innovation, or we call it industrial AI, is going to be something very similar. So right now we're having like this, 5,000 square meter facility, and we are building it to do this, right?
How much does that cost?
Hundreds. Well, it can cost anywhere between, if you're very smart about it, a few tens of millions to hundreds of millions, right? So some of the companies who raise hundreds of millions, they are trying to not per se build the gigalabs. They're actually still focusing on generative AI. But these facilities can be as complicated and sophisticated as you want, or as, focused on certain verticals and modular as you want. So the way we're trying to do this is that we're trying to build a modular. We are trying to build the smallest facility that you can have in order to have these tenth of thousands of data in a short time period. It's an expensive facility.
Well, if that's a real kind of moat in the industry, if data is really the thing that unlocks the rest of the industry.
Yeah.
That doesn't seem like a crazy amount of money to me.
Yeah, but you still have to have people believe in it, right? So we're still like, so many people are still debating about, okay, I'm just going to use AI only. I'm going to use a simulation of screen only. So it's kind of like people who have been through multi-disciplines, yes, they know this. So we realize that we need all of that back in 2022. But also this field of full of, people who did only AI, right? People who did only batteries. And they think like, a typical battery laboratory is the one that you need, you don't need AI for these kind of things. And others who think that, you only need simulation. So kind of like there is a lot of knowledge and teaching and education that you actually have to give thought leadership in the market, and part of what we are doing today to be able to actually get that direction that people actually believe ultimately it's a data problem. It's a high quality, highly standardized data problem. We don't need much better AI models. Actually, in fact, the AI models that we have 2 years ago are probably much better than the AI models that we had today for actually being trained on these data. So the AI models level, they're actually quite good already. Simulations, you need still to upgrade the simulations much more. But actually, ultimately, what you want to have these very standardized facilities to be able to generate these tens of thousands of industrial grade level data to be able to actually train the AI on. And that's what people are started to realize.
That's probably a good segue to start talking about the business model around all of this, because obviously you're not a research lab, you're not financed by
Yes.
public money, or maybe partly, but at least you have a lot of private capital.
Yes.
How do we build a business around what you're trying to do today?
Yeah. So there are several standard business models that you can use today to capitalize on this. And there are some business models that you can actually, copy or imitate from adjacent markets. But there are also whole new business models. That's my expectation, that there will be whole new business models being developed when this actually field matures. The current business models that you can have is at least what Dunia is doing. What Dunia is doing today is co-development or co-innovation. So we work with companies who are interested in this field. We don't do CRO. We don't do contract research organization kind of thing. But we are actually heavily invested in what our partners are working on, and we reap the rewards together. So kind of like whether it's an IP or material that we actually scale and so on. And there is this business model. There is another business model where we are ourselves actually work on, we have our own internal pipeline of things that we are very much interested in, high risk, high reward kind of things. And we already had, 2 breakthroughs. I can talk about that later. One of them was actually quite interesting. It was the first AI discovered catalyst that we had. It's a very funny story, actually, very interesting story. And we licensed that, right? So you kind of like, and that's actually a very standardized business model today. EPC companies use in the energy industry.
So
right?
wait, you're saying that you have actually already discovered one new material that is stable, usable, has value for the industry?
Yes, we actually have patented 2. So one actually for electrocatalysis in general. It happened to be the topic of my PhD, but I had no expectation or didn't actually expect this formula that I saw that day would actually do this process. And the other one was actually for semiconductor substrate materials. We'll talk about that later. But yeah, if you want to know, I mean, the first one was actually quite interesting. So we are running campaigns in the company, internal campaigns. So we do external campaigns. So we work with companies and very interesting companies as well, very large companies in the world, BASF, Altera, and others, to do a lot of things that they are interested in or we jointly interested in. But we also have certain processes that we run campaigns internally to try to understand, unlock breakthroughs there. And then we were in one of these meetings and people were like, the technical team was showing the results of, different catalysts doing, actually producing hydrogen, over potential, still over potential looks like this and so on. And then I was looking at this because I did my PhD in the topic, so I kind of have personal interest in trying to understand what's going on. And then I saw a formula that doesn't make any sense. I was like, okay, so I asked why do you have these 2 elements in that formula? And people were like, what do you mean? It's the prediction that the reasoning model actually came up with, and we basically executed it. I was like, okay, so that shouldn't be there. Like from the knowledge I have, on that field on hydrogen production, that shouldn't be there. And then show me the results. So we started looking at the results. The results are very interesting. So much lower onset potential for this device. It's actually quite a stable system as well. It's equally efficient or sometimes even more efficient. And the most interesting part is that it exists, like imagine the search space looks like this. Everyone is looking at the bottom part of the search space. The top part of the search space, people have tried a couple of things, but they found out that the elements there, these formulas are not very interesting. What the reasoning model, what the AI did is that it actually optimized different elements in the formula until it found one of them that could be interesting, and then it recommended this one. And it happened to be that this one in the middle of all of this sea of inefficient catalysts was actually quite an efficient one. So we kind of like, we were dazzled by this, and it was like, okay, like we are gonna design a campaign for that one to optimize it and see how it looks like, and we patented it. So there's gonna be a lot of announcement on that one later, but we're trying to do a lot of optimization internally.
What's fastest path to revenue from there? So basically, now you have a new material.
Yeah.
You were talking about the first model, which is like a co-research or co-development of new material. But
Yeah.
right now you're saying basically we didn't have any customer for this, but we've built it anyway. How do we get to revenue from there?
Yeah, so we already started actually, and we already have a commercial project with a company that's have the most advanced electrolyzers today for hydrogen. It's a company from Spain, Mateco. Very interesting company. And they saw what we were doing. They were actually very, very much interested in this, and we started actually a commercial project to dive there deeper and potentially have IP pairing contracts there. And so there's a lot of negotiation in this direction. We had a first project with them, but we're also talking to so many different companies who are interested in seeing more about this. So that's what I mentioned earlier as the IP licensing model, right? So kind of like companies who come in, they like your formula, they have a process, but they think that there's something that could be interesting for them there. As they want to license it, they give you an upfront payment. Usually it's in the millions, right? And you get a percentage of the revenues on an annual basis, even during scale up of this process. The problem with industrial R&D in general is that we didn't have a problem with building something that's scaled up. We had a problem with a brutally inefficient innovation cycle, right? So in the last 75 years or so, since 1950, we had in the industrial R&D, we had only 12 to 18 breakthroughs.
Mm-hmm.
If you take these numbers and look at the R&D budget for industrial R&D, that was $15 trillion since 1950. So that means that each of these innovations actually cost the world something like $1 trillion. It's a highly inefficient way of actually doing industrial R&D. So we are tackling this part, right? The scale up, once you actually find something that's already close, TRL 5, TRL 6, close to scale up, taking it from TRL 6 to TRL 9 still requires some work, but it can be way faster than taking something from TRL 2 to TRL 6 or TRL 7. And that's why we always say, like, in the company, we try to test things at the end of TRL 5 and TRL 6, because anything lower than this is not useful for anyone. So so that's one of the models. There are also other models that the world haven't even thought about it yet, right? So these data themselves are extremely valuable. So people are actually coming after these data. They want it. You can use it for training the models. So there's a material business model. There's a data business model. There are new processes business model. But what ultimately actually Dunia is looking at is creating different inflections, creating different breakthroughs of chemistries that we didn't even know existed yet, right? So that is actually our dream. When we started doing this, we didn't do it just to have one material breakthrough. We did it because humans don't understand how 2 or 3 materials together look like and what they can do. If you put 5 or 6 or 7 elements together, that's beyond our understanding today.
Mm-hmm.
These new approaches that we are developing, AI for materials, or call it industrial AI, potentially can enable us to understand beyond that. And this is where I think sky's the limit.
This is why it gets you excited.
Absolutely. Absolutely.
In a world where Dunia works out pretty well, if we think about climate tech, what's the result of Dunia? And what's the impact of Dunia in the world if it works out?
Yeah, so that's actually quite a good question. So when we started doing this, we started from a climate tech lens. I was, a technology manager scaling up climate tech technologies in the energy industry, and I saw firsthand the problems that we are facing there. And people sometimes outside the energy industry, they criticize the energy industry a lot, like, oh, they are lazy, they don't want to do this, and these. Believe me, everyone inside, they actually want to do this, because if it worked, they will be able to capitalize on both worlds, a world where the current fossil fuels are still working and a world that actually where they can transition. But the problem is these systems, the climate tech technologies that we have today are very, very energy inefficient. There are a lot of reasons. I can happy to expand on this later, but for this to happen, why is it like this today? And so that's actually the lens where from which Dunia started. So we started saying like, okay, we want to use this technology, this approach, to look at climate technologies and try to speed them up. That's one of the reasons why we had a lot of use cases. I always talk about hydrogen. I talked about CO2 conversion. These are the things that we actually did in the first few years. We expanded from there to other applications, more established thermocatalysis and batteries and semiconductors, other things like that. But climate tech has always been at the heart of what we are doing, and actually the most successful use cases that we had so far. What we as a company want to do is that we want to reduce the energy barrier for things like hydrogen to be produced. One of the things people are always saying like, okay, green hydrogen is not efficient mainly because of electricity consumption. That's true. Electricity consumption there to make hydrogen is actually like between 50 to 70%. But why
of the final cost?
Of the final, yeah. But why is the electricity consumption of making hydrogen so high? Because the materials in an electrolyzer that are actually used to create hydrogen are not designed to create hydrogen. And that's also not something very, very interesting story I can tell you about that. When we started doing all these energy transition things, these processes are based on still catalysis, right? So catalysis is this kind of like invisible material that looks like a drug, right? It's worth like a drug, billions. Once you find it's a brain that actually enables a chemical process to happen. We had in the fossil fuel world, we have something called syngas, right? So we have like hydrogen, we generate hydrogen from natural gas, we burn it and we generate hydrogen and we generate CO, carbon monoxide. And then you run these over catalysts to actually create hydrogen from them. And you create also CO2 and you create water and so on. What people try to do in the energy transition is that, okay, let's just take the same catalyst and try to convert water and CO2 into something, like break down water into hydrogen or break down water and CO2 into syngases and other things. The problem with this is that the chemistry of converting water is very different than the chemistry of converting just, like elements like CO and hydrogen into other, chemicals. So, sorry, I mentioned earlier, like we burn natural gas to actually hydrogen and CO, and then we convert them, that's the syngas, and we convert the syngas into other chemicals on carbon, copper and zinc oxide. So when people actually try to take these elements and to convert water and CO2 into these, chemicals, green chemicals, these catalysts don't work anymore. And then you need to inject a lot of energy to actually make them work. And that means that what you create at the end is quite expensive, because water and CO2 are very inert molecules. They come at the end of the chemical process, unlike hydrogen and CO that are actually highly active molecules. So a catalyst have a much easier job. But if you can speed up the discovery cycle and come up with catalysts that can reduce that energy barrier for converting water and CO2 much faster, then you can actually reduce the electricity that are needed for hydrogen, for green hydrogen to be produced, and that enable it to be much more efficient and potentially competitive with fossil fuels as well, or gray and brown hydrogen and so on. So that's what we are doing, and that's one of the catalysts that we patented is trying to do, going into that direction.
So hydrogen was never going to be able to work technically the way we produce it, the way we do now, basically.
So yeah, speaking frankly, when people start to innovate things, there's always a period where a lot of money is injected into a certain market. With that money comes a lot of people who are working in the right way of actually scaling up a technology and innovating, but also a bunch of companies, a bunch of approaches that are just hype driven, right? And then what happens usually is that this hype cycle goes down and then the real science starts to pick up, right? And that's what happened in solar. That's what happened also in new types of batteries as well. And my prediction, it will happen with hydrogen. So hydrogen is going to pick up. I think my expectation is that you will have a lot of different directions to make very efficient hydrogen, green hydrogen, and other types of hydrogen. But you have to abandon, the hype and focus on the science and then try to speed it up and scale it up much faster. In solar, we had exactly the same story. People are saying it's too expensive, it's never going to work, I will never have this solar thing looks ugly on top of my house and all these kind of things. And now solar is so efficient that people are actually complaining that it's too cheap, right? So it's always the same. It's always the same with innovation.
Do you think we can unlock efficiency for solar panels through material discovery?
Absolutely. I think it's this field is ripe for for innovation. So people are talking about perovskites doing much more efficient solar systems right now, 30 to 35% efficiency. These things actually were just dreams 20 years ago, right? Silicon's still the king, right? But there are so many different elements. Germanium is very interesting and others. So I think there is a lot of interest there. We are ourselves in a lot of discussions right now with some very interesting, market players in the space who wants to see how they can use this approach to actually scale up and speed up how they develop new materials for solar panels and solar technology. I think there's still a lot of innovation in solar, but it's going to be much more, not just much more efficient, but also hybrid with other things as well.
All right, so we're getting towards the end of this episode, but there's maybe something I want to ask you about, which is to extrapolate a little bit in the future. What is the vision for Dunia? Where do you want to be 10 years from now?
Well, that's an interesting one. There's, of course, the internal vision that I'm keeping internal. No, but yeah, so it's just, the dream that always we have been dreaming about when we started Dunia, and the culture actually that we built internally is that we want to see all these breakthroughs being developed and being realized as fast as if you're actually developing an iPhone or a Samsung phone in a factory, right? Like you want to have this, and that's a vision for Dunia. That's how we dream about it. An engine that enable all these discoveries to go in a much more, designed, predictable way, and being scaled up faster. I think it's not acceptable that we have one industrial, breakthrough innovation in 20 years. It's not acceptable that we have only 18 in 70, 80 years. It's the world, used to innovate way, way, way faster than we are doing today, and that's not happening fast enough anymore. So I think that's one of the dreams that we have at Dunia, right? How we can actually make this approach work, and how can we make other people use it more? We need more companies like Dunia doing what we're doing. But then we have even a grander vision than this, right? So kind of like I had, it's kind of like almost a childish dream, right? But I think we have to dream of it in order to achieve it, which is, I mentioned earlier that what happens if this approach worked, when this approach works, and then you actually unlock elements, or unlock formulas, not elements, but unlock understanding of different elements being put together, right? New chemistries that we didn't even know about. There are a lot of things that we are thinking about and dreaming about today. All these kind of like polymers that you can code, that you can program, that are way more conductive, like an almost impurity-free catalyst or semiconductors. These are things that are just dreams today, and they are dreams because we couldn't unlock the chemistry behind how you can actually achieve that. In 10 years from now, if we unlocked some of these inflections that themselves go on and create different industry breakthroughs, that's going to be amazing. But then, if we can make some money out of that as well, that would be great. I mean, money is, of course, you build a company to make revenue and to make nice profit margins. You never actually dream about making the money. You dream about something big. Usually that's a reflection from your childhood, and then your whole life is actually about achieving it. And that's what Dunia is doing today, right? That's not only me, but also Alex and Marcus, the other co-founders, thinking and dreaming about. And we decided to actually build that culture in the company, right? The culture of people who have this grand vision, who believe in a breakthrough, and guess what? It actually attracts a lot of people around the world. So we had people working with us from Asia, from Singapore, from other places, of course from Europe, but also people from Canada relocating to go to Berlin. People from Hawaii working with us. They had other companies in the US there as well, but it's the vision and the dream. And, when you come and see that actually these people believe in it and they want to achieve it, that is actually priceless. That you cannot put a price tag on this, and it makes us wake up in the morning thinking, when the next breakthrough will be? Is it today, tomorrow? That moment when we found out this new catalyst, new formula. Can we have these? Can we have these more? Because it's such a priceless moment that people actually talk about for decades to come.
Do you want to be remembered as someone that has invented new materials?
So the founders, usually we sit together, we talk to each other a lot, right? And we have these personal moments sometimes where you talk like, okay, what do you dream of? What do you want to do? And each of us, they have this kind of like dream and vision. And like the guys asked me the first time, like, what do you want to do? Why do you actually do this? Why did you leave a very stable job and you have a family and kids, like to actually start up something? And the answer was exactly this. Like, I want to have a legacy. Like when I leave the world, I want people to remember, mainly my kids actually, to take that as a kind of like a model that, oh, you want to do the same thing, right? There's something that this person, did, or that company was actually quite successful at. We still talk about Bell Labs today, although it's actually ceased to exist for a while, right? Or not as successful anymore, that model, right? Because they had a huge legacy, that legacy affecting us. Actually, this legacy is the reason why we can have this podcast today, right? So, yeah, I mean, that's, dream of mine, personal one, selfish one, that I leave a legacy that people will be proud of, mainly my kids and my wife and my family.
I love that. And what I love about it is that drive by the vision, by the impact on the world, rather than the drive to make $1 billion company. Although that's probably a result of, building a great company is just like having a large valuation. I also wish that, Dunia becomes the first $1 trillion company for Europe. Maybe that's the thing. Let's see what you can get. But look, this was a fantastic discussion. Couple of last questions. You mentioned 2 books that are interesting earlier in this conversation. Can you remind me what they are and why you like them?
Yeah. So as I told you earlier, like I'm reading a lot these days because I'm taking the plane a lot these days. My back hurts a little bit of sitting on the plane these days. So Pattern Breakers, I highly recommend it for anyone who's watching or listening today, by Mike Mabels. It's a small book, but it's actually looking at something very interesting. It's looking at companies, founders, startups that actually succeeded in capitalizing the market. So back then they invested in Uber, they invested in Twitch and all these kind of very successful companies today. And so he was looking at why these companies succeeded and why other companies who were trying to do the same thing failed, right? And he was going into this phenomena of that these companies actually captured market inflections, right? When you have, a GPS being implemented in iPhone, I think it was iPhone 6, I'm not sure, that enabled us to actually, locate our location in the map and order Uber, right? And Uber capitalized on this, so that's kind of like they capitalized on inflection and they created a breakthrough. Same with Twitch, you have better cameras, you can screen more, you can stream more and so on. So he was looking at this, a highly recommended book. And then of course the Idea Factory, I think it's just an amazing book. It was looking at the innovation cycle of Bell Labs back then in 1950s and 1940s, when you have this big building, you put all these different disciplines together and you design the building in a way that all these different disciplines keep actually, bumping into each other, basically, keep coming back to each other. They stand at the water cooler and all these kind of things. And this is actually, it's funny enough, when you go through the book, this is where many of the innovation happened. They were talking about a different topic and someone was just listening. I was like, oh, wait a second, you're using this material for that thing? Can I try it? And then you have a semiconductor. It's amazing. It's much bigger book though, so you need some more time for that.
Fantastic. One last question for you, maybe the toughest one today, but who do you want to see in an interview next in your seat for the podcast?
Difficult question. Yeah, we are in Paris. So if you can get Jan LeCun, I think would be great. I would love to hear his thoughts of what he's building today. We're actually quite excited about what he's building because, we were chatting before we start about LLMs and at the beginning of the podcast as well. LLMs are very interesting in general. We have seen great uses. It's not there yet for material and scientific discovery. We also internally don't really fully believe that we can only use LLMs for that. So you need to use other tools as well. And Jan's thinking also in a very interesting direction. We are developing something that also, complements and adds to more and more to LLMs there. So I'm gonna keep that internal, but I think I would be looking forward so much to a podcast like that.
I will try my best. I think it's going to be difficult, but let's see.
Otherwise, you can always bring, an EU venture capitalist in the deep tech space and try to tell them like, oh guys, you can also take some more risks there. But let's see. I'm looking forward to the next one already.
Fantastic. Well, thank you so much for today's discussion. It was fantastic. For listeners, if you like this episode and if you like the show, don't forget to like, comment, and subscribe if you're on YouTube, or to give us a follow and a 5-star review on Spotify and Apple Podcasts. It takes 2 seconds. By the time I finish that sentence, you will be done with it. Fantastic. Thank you so much, Ahmed. It was a perfect conversation. I loved it. Thank you so much.
Thank you very much, Hugo. Guys, subscribe. Do it, please. Do it now.
Fantastic.
Thank you. Bye.